Welcome to today's lecture. Today we are going to continue from where we had left in the previous lecture. In today's lecture, we will learn how to experimentally determine the elastic stiffness parameters of soil, and in particular we will learn how to obtain the coefficient of elastic uniform compression, that is CZ. In order to measure the elastic dynamic parameters of soil, we need equipment which can impart dynamic forces on the soil, and also we need sensors which can accurately measure the dynamic response. The most important dynamic response which needs to be measured is the displacement and the acceleration. Let us first talk about the equipment required to induce dynamic forces. These equipment may work on rotating or linear vibration principle. Let us first see the equipment working on the rotor principle. Typically, such equipment consists of a pair of rotors which are synchronized, that is, they undergo rotation with same angular frequency but in opposite sense. The net effect of such rotations by this synchronized pair of eccentric masses is that the net force is generated in one particular direction as shown here. Now we can also change the direction to horizontal by suitable orientation. So whether horizontal force or vertical force, both can be generated by this kind of rotor principle. So here the combination is applying the force in the vertical direction, but in any of the directions force can be achieved by this principle. The other principle is that of electromagnetic induction, also called as the electrodynamic shakers. In this kind of equipment, essentially a linear vibration is produced, and these equipment are commonly called as shakers. Now these shakers are very commonly used in model testing of structures. For example, a typical arrangement is that in the industry, these shakers, they are connected to the structure to be vibrated by means of an element called as stringer, and by their vibrations the structure to be tested is made to undergo vibrations. The other end of the shaker is fixed to the ground. Now an alternate arrangement based on the inertial principle is also possible. So here there is a base plate which connects to the ground or the structure to be vibrated, and the main shaker is positioned on the top of this base plate. Then a number of stringers, they connect the shaker, the main vibrating element, with a top plate, and the top plate is held in position not alone by the stringers but also at least 4 springs which are positioned in between the top plate and the base plate. So the action of the shaker makes the top plate undergo vibrations. So by inertial effect, force is produced. Let MP be the mass of the top plate. So essentially, in order to create the desired type of vibrations, the vibrations could be of different types. So we need a function generator which can generate the desired signal. It could be sinusoidal or it could be a random signal. The signal is then transferred to an amplifier which amplifies it, and then this amplified signal is transmitted to the shaker. The shaker has a special coil called as armature coil, and this is the main element of the shaker. So when the vibrations are happening, we need to measure the acceleration of the top plate. We already know its mass, so if we are able to measure the acceleration, then we know that the force acting on the top plate is mass times the acceleration, and opposite of this force acts on the structure on which the shaker is mounted. So this is the principle of measuring the force. Now the next measurement related to vibrations is the measurement of acceleration at the base of the shaker. So this could be the floor or it could be the machine foundation. For this purpose, we may install an accelerometer at the base as shown here. So this basically measures the response and the vibrations induced on the host structure or the floor. So we basically measure the acceleration, and then if we want to convert it into displacement, then all we have to do is use the relationship between displacement and acceleration in the case of harmonic vibrations. So from the acceleration amplitude, the displacement amplitude can be obtained as acceleration amplitude divided by omega m square, where omega m is the angular frequency of the applied vibrations by the shaker. So this is the indirect method of measuring the displacement. We can of course measure the displacement directly also. However, it is bit difficult in the case of dynamic situations. If we are very much intent on direct measurement of displacement, then there are 3 different technical possibilities. The first type of sensors are analog type sensors. So essentially these are basically dial gauges, and here the measurement is to be made through the dial gauge principle, but in dynamic situations this could be difficult. The other type of sensors are the ones working on the resistive principle, that is, they are based on the principle that a conductor, its resistance is a function of the induced strain. So if the conductor undergoes strain epsilon, then the relative change of resistance is directly proportional to the induced strain, and the two are connected by the constant called as gauge factor. So most of the electrical strain gauges they work on this principle. Then the third type of measurement is the electromagnetic type. So here the principle used is that of electromagnetic induction. So essentially it consists of a pair of coils, and these coils usually overlap each other. So in the primary coil, which is the main or the stationary coil, a potential difference is applied, and then in the case of the second coil, the potential difference is induced by means of electromagnetic induction, and that coil is called as the induction coil. So if we are applying, say, Vi across the main or the stationary coil, and if Vo is the voltage induced across the induction coil, then the induced voltage or the output voltage depends on the length of overlapping. So usually the induced voltage at Vo is calibrated with the coil length, which is overlapping, and in other words this is correlated with the displacement. Now, having learnt about the equipment and the sensing systems, let us learn how do we determine the coefficient of elastic uniform compression, CZ, of soil. The related procedure is very well described in IS 5249. There are two ways of measuring CZ. One is the direct method and the other is the indirect method. Let us first study the direct method. Now, some of the preparations are same for both the direct as well as the indirect methods, and they will apply to both. So essentially the first step is that we have to dig excavation at the actual site where the machine foundation is proposed to be installed, and it should be dug with same depth as for the actual foundation. And then at the base of the pit, a specified concrete block is placed. So this is the bed block. As per IS 5249, the concrete block should be of M15 grade. It is supposed to have very specified dimensions. It should have a length of 1500 mm, width of 750 mm, and a thickness of 700 mm as shown here. So the dimension with 1500 mm should correspond to the rocking vibrations. Hence this longer side should be in the X direction. Of course, Z is the vertical direction, and the 750 mm length should be along the Y direction. Now on the top of this base concrete block, the shaker is to be positioned. It could be either the inertial type shaker using the electromagnetic principle or the electrodynamic principle, or it could be the rotor type dynamic force generating machine. So here we are describing the measurement using the electrodynamic shaker type equipment. So for that purpose we need to measure the acceleration at the top of the top plate and also at the base block. So let AP be the acceleration of the top plate as shown here and AB at the base block. So we need two accelerometers to be installed as shown here. Now the shaker should be positioned such that there is no eccentricity involved. So here pure vertical vibrations are generated. Also it should be made sure that the ratio of the dynamic force to the static mass of the system, this ratio should be as per the actual scenario. So here the dynamic force can be easily calculated by means of the product of the mass of the top plate and the corresponding acceleration. So that should be suitably adjusted. So let the omega m be the angular frequency of the actual machine. Now we need to determine omega n, that is the natural frequency of the experimental block and the soil system, but it is not that of the actual proposed foundation. Now let m be the mass of the block plus the shaker system consisting of the main element and the springs and the top and the bottom plates. So the procedure involves excitation of the shaker over a very wide range of frequencies such that it passes through the natural frequency of the system meaning the experimental block and the soil. So the objective of this exercise is to determine the resonance frequency of the machine foundation system in this particular scenario. So all we have to do is we excite the shaker at different frequencies and plot the acceleration observed at the base as frequency of the induced frequency, and what we will find is that plot would look something like this, that it will show a peak at a particular frequency of excitation. So what we are measuring is the amplitude of the acceleration of the block at various frequencies. So this would be the natural frequency of the foundation soil system for this particular case, but it should be again noted that this is not the natural frequency of the actual machine foundation system. It is referring to the particular system comprising of the small block and the shaker here. So once we have obtained the natural frequency of the experimental system, then we can obtain Kz of this particular system by the product of the total mass and the square of the angular frequency, and from the stiffness we can obtain Cz by dividing with the area of the block, which is 1.5 by 0.75 meter square. So this particular CZ is measured for this small experimental concrete block representing the block type foundation. So it needs to be corrected because the actual foundation shall have different size, so size factor comes in. So this is corrected as shown here. So basically we need the actual foundation area for this purpose. So this correction factor has to be applied subject to a maximum value of foundation equal to 10 meter square. So we can observe that CZ is inversely proportional to the size of the foundation block, and here we are plotting the ratio CZ corrected to CZ measured with respect to the foundation size, and we can see the variation. So essentially the small block used for connecting this experiment, it has the size of 1.5 by 0.75 meter, which boils down to 1.125 meter square. So up to 10 meter square of area, the variation is the way it's shown here, and after that the correction factor is deemed to be constant. So then the size effect is more or less saturated. Now here what we have to do is we have to keep changing the frequency of the exciter one by one and wait for steady state vibrations and then measure the amplitude of the acceleration induced. Now there is a faster way. The faster way is that we can apply the signal in sweep form as shown here. So sweep signal means that we are changing the frequencies linearly with time. Say within a very short span of say 10 to 100 seconds, we may very rapidly change the applied frequency, say from 5 Hz to even 100 Hz. So this sweep signal can be applied in a single short manner across the shaker to make the block vibrate, and then we can measure the time response of the induced acceleration at the top of the base block, something like this. So the time domain response can be converted into frequency domain response by means of the fast Fourier transform. You already know how to use MATLAB for this purpose. Once we draw a plot of the measured acceleration as a function of the frequency, we can very easily capture the resonance frequency in the form of the peak. So as compared to the other method of applying the vibrations, this is quite fast and expedient in application. Using the same plot, we can even obtain damping parameter of the soil, that is the damping ratio. So you have already learned in your structural dynamics course the half power bind method of obtaining the damping ratio. So all we need to do is that we already have the peak value of the acceleration response, and that corresponds to omega n. For this purpose, we find two more points such that the corresponding power is half. So for that purpose, we choose the points at 1 by root 2 of the peak amplitude, because for that condition the power would be half. That's why this method is called as half power band method. So we are showing these frequencies as omega 1 and omega 2 here. So delta omega is the band where the power is in this particular range. So if we have these frequencies, then the damping ratio is given as delta omega by 2 omega n. Now let us also study the indirect method of measuring CZ. Many of the procedural steps are common with the direct method we have studied. Essentially, we need to dig the pit in the same manner and utilize the same concrete block of dimensions 1.5 meter by 0.75 meter by 0.7 meter for this purpose. So we create the pit and then place the concrete block in the same manner, and after this we set up the shaker system, which could be either the rotor type or the electromagnetic type. So here we are again showing the electromagnetic type only. In the previous case, we had measured two accelerations, one of the top plate, which helped us in calculating the applied force, and then we also measured the acceleration at the top of the base concrete block. Here the difference is that instead of measuring the acceleration at the top of the base block, we install two geophones directly on the soil. So basically, geophones are the sensors which detect vibrations of the soil. Now the typical distance of the first geophone from the block should be around 300 mm. So we start the vibration system, and the shaker system here is made to operate at omega m, which is the operating frequency of the actual machine. Using oscilloscopes, we measure continuously the signals received from the two geophones, and we adjust the distance between the two geophones such that we are obtaining the two signals from S1 and S2 in opposite phase as shown here. That means if one of the geophones is just about to undergo the displacement in the upward direction, the other one is about to move downwards. If this is achieved, that means the separation between the two geophones is exactly half of the wavelength. Hence, wavelength can be obtained as 2 times the distance d separating the two geophones. So once we have this wavelength, then all the calculations, they become very easy for us. So we can obtain the wave velocity from the measured wavelength as the product of the applied frequency and the measured wavelength. So applied frequency is basically same as the frequency with which the actual machine is supposed to operate. So please note that here this is the frequency measured in hertz and not the angular frequency in radians per second. We know from mechanics of solid that the wave velocity is related to the shear modulus, and the corresponding relationship is this one, that is, it's the product of the density and the velocity square. So once we have the shear modulus of elasticity, then the Young's modulus can be obtained very easily by making use of the relationship between the two, that is, the Young's modulus is 2 times the shear modulus multiplied by 1 plus mu, where mu is the Poisson's ratio. We can make use of the Poisson's ratio depending on the soil type from the literature. The typical value of the Poisson's ratio for clay is around 0.5. For sand, it varies from 0.3 to 0.35, and in the case of rocks, it's a bit low, in the range of 0.15 to 0.25. So the appropriate value can be used to get an estimation of the Young's modulus. And once we have the Young's modulus, then the coefficient of elastic uniform compression is related to Young's modulus by this relation. Here alpha is an empirical correction factor, and B and L, they are the actual foundation dimensions, B being the width and L the length. Once we have measured CZ, we can obtain other elastic constants of soil by the empirical correlation factors. So C tau, which is the coefficient of elastic uniform shear, is half of CZ, and C theta, which is the coefficient of elastic non-uniform compression, is 2 times CZ, and C phi, which is the coefficient of elastic non-uniform shear, is 1.5 times C tau, or 0.7 times CZ. So the measurement of CZ gives us an estimation of all other coefficients also. So we will make use of what we have learned today in the coming experiment, which will be performing in the lab on how to measure CZ of soil. So thank you very much. If you have any questions, you can discuss them during our interaction in the MST.